Hey everyone, welcome to this explainer. Today, we're going to decode something absolutely wild that's happening literally every single second around the globe. We're looking at how humans and machines bridge their massive communication gap using the fundamental building blocks of number systems. Have you ever actually stopped to think about how your abstract thoughts and human math get translated into the physical hardware of a computer? It's like a giant puzzle. Well, that translation process is exactly what we're going to unpack today, so let's get into it. So it all really starts with a very basic, very human question. Why on earth do we count in tens, but computers count in twos? Well, we naturally count in tens, likely for the very simple evolutionary reason that, you guessed it, we have 10 fingers on our hands. It's completely built into our biology. Computers, on the other hand, they operate in an entirely different, kind of alien reality. They don't have fingers, they have circuits. And because of that, they require a totally different language to function. You see, to a desktop computer, information isn't an abstract concept or a squiggly line drawn on a piece of paper. It's processed entirely as electrical signals. And those electrical signals are wonderfully, almost brutally simple. They are literally just either on or off. That's it. Now, this hardware limitation creates a massive problem for our native 10-digit math. We have 10 concepts for numbers, right? But the machine only has 2 physical states to work with. Okay, so here's our secret decoder ring manual for today. We'll start by looking at why we need different systems. Then we'll define radix and base. After that, we'll explore binary, octal, and hexadecimal, check out the relationship matrix, and finally, learn how to convert decimal to binary. We're basically going to build a bridge between our human reality and the digital universe. All right, jumping right into section 1, why different systems bridging the gap? So, to truly master our digital tools, we first need to accept why computers just can't use the numbers we're so comfortable with. Honestly, the core of the issue here is efficiency. As humans, we need a really broad representation of numbers to navigate complex daily tasks. Things like finance, measurements, science. We need a system that represents numbers in a compact way that our brains can easily digest. Computers, though, they require vastly simpler hardware states, so they can process literally billions of calculations a second without a single error. So we rely on specific mathematical systems to bridge this gap. We essentially scale from our native decimal system all the way down to binary, octal, and hexadecimal systems just to feed the machine exactly what it needs. Moving on to section 2, radix and base, defining the core. Before we go learning a completely new mathematical language for machines, let's quickly deconstruct the system we already use every single day. The really crucial point to remember here is that whether you hear the fancy mathematical term radix or just the more common term base, they mean the exact same thing. It simply defines the total inventory of unique digits a specific system has to work with. Oh, and a quick heads up, that inventory always includes the digit 0. Now, because we only have limited inventory of digits, we have to use a positional value system. We already intuitively know that a number's value fundamentally changes based on its position, right? Let's look at 3 quick examples: 734, 971, and 207. In that first number, the 7 represents 7 hundredths. In the second one, it means 7 tenths, or 70. And in that final number, it's just 7 single units. It's the exact same digit, but it has a radically different value based entirely on where it sits. And this perfectly illustrates our base 10 decimal system. It proves that every single position in a number is, at its core, just a digit multiplied by the powers of its base. Think about it. Starting from the right, the first position is 10 to the power of 0, which is just units. Move one spot left, it's 10 to the power of 1, or tens. Move left again, 10 to the power of 2, meaning hundreds. This is literally the structural framework of the math you use every single day. Let's jump into section 3, binary, octal, hex. Computing languages. So, now that we've got that universal structural rule of positions and bases locked down, let's go ahead and swap out our human base of 10 for the actual languages of computing. First up is the base 2 binary system. Because it's base 2, we're only using 2 digits, 0 and 1. Remember those on and off electrical signals we talked about earlier? Well, this is exactly where they live. But check this out. The positional rule remains beautifully, perfectly identical to our decimal system. The only difference? Instead of powers of 10, we're just utilizing powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, and so on. Now, what's actually really interesting here is the anatomy of a binary number itself. Because every binary digit is called a bit, we actually have specific names for their positions. The leftmost digit carries the most mathematical weight, so it's called the most significant bit, or MSB for short. The rightmost digit carries the least weight, making it the least significant bit, or LSB. If you're getting into computer science, this terminology is absolute standard practice, for sure. Okay, let's move on to the next system and see how this builds into a slightly more complex way to represent data. This is the base 8 octal system. As the name probably gives away, it uses 8 unique digits, running from 0 through 7. And, just following our universal rule from earlier, the weight of each position maps perfectly to powers of 8. 8 to the 0, 8 to the 1, 8 to the 2 as you move to the left. And finally, we have the base 16 hexadecimal system. Now, this one is wildly efficient, but it definitely requires a slight mental leap. It needs 16 unique digits, right? So it uses our standard numbers 0 through 9. But then it completely runs out of single-character numbers. But instead of giving up, it gets creative. It introduces the letters A through F to represent the values 10 through 15. So the letter A equals 10, all the way up to F, which equals 15. And as always, no surprise here, its positional values are just the powers of 16. Bringing us to section 4, the relationship matrix, comparing the bases. I know it might feel a bit overwhelming to juggle 4 entirely different bases in your head all at once, but comparing them side by side reveals this amazingly clean mathematical harmony. Just take a look at how a standard human decimal number 15 translates perfectly across the board. In hexadecimal, it's just a simple single-character F. In octal, it requires 2 digits, becoming 17. And in binary, broken all the way down to its most fundamental machine states, it takes 4 bits, 1, 1, 1, 1. Honestly, this matrix is basically the Rosetta Stone of computer science. And our final section, section 5, decimal to binary, the conversion process. Let's wrap this up by giving you a tangible, practical skill. Essentially the translator's ultimate tool for turning our human math directly into machine language. We're going to use what's called the repeated division by 2 method. Let's take the base 10 decimal number 73. So you divide 73 by 2, which gives you 36, with a remainder of 1. You just write that 1 down. Then take the 36 and divide it by 2. That's 18 with a remainder of 0. Write the 0 down. You just keep dividing the new quotient by 2, all the way down until your quotient hits 0. Once you're done, here's the secret trick. You read your list of remainders from the bottom to the top. The bottom number is your most significant digit, and the top is your least. Doing this for the number 73 gives you the exact binary sequence of 1001001. Boom. You literally just translated a human thought into a machine command. How cool is that? It is absolutely staggering to realize that this incredibly simple process, literally just repeatedly dividing by 2 and tracking the remainders, builds the absolute foundation for all the world's software, every smartphone in our pockets, and every global network. It really leaves us to wonder, if an entire digital universe is built on nothing but zeros and ones, what other complex, seemingly impossible realities can we decode just by taking the time to understand the base? Thanks so much for joining me on this explainer, and remember to always keep questioning the systems around you.